Formally, we'll define the derivative of a vector function like this. Let the position vector r have the components fi hat, g, j hat, h, k hat, where f, g, and h are differentiable functions of t. Then our vector has a derivative on the interval ab and is given by r prime is equal to the derivative of the function f, I hat, plus the derivative of g, j hat, plus the derivative of h, k hat, provided that the derivative of our function does not equal the zero vector. If that's the case, then we could say the derivative r prime is a tangent vector at the point corresponding to r of t. Well, let's unpack this a little bit. First thing we're saying, or a first constraint, is that our derivative vector cannot be equal to the zero vector. So in other words, the derivative of our vector function cannot have components that are each equal to 0 simultaneously. We cannot allow that. Why do you think that we can't allow that? Well, the reason why we can't allow the derivative to be equal to the zero vector, it's because there would be absolutely no change if that were true. Well, for example, if this is based off of the limit as delta t goes to 0 of delta r over delta t. If we allowed the derivative vector to be equal to the zero vector, and again, I'm saying we can't allow that. This is a hypothetical. If r prime was equal to the zero vector, then that would mean that our delta r, the change, was equal to the zero vector. In other words, there would be no change in our position if the derivative was equal to 0. So to just illustrate that, if this were our curve, and here's point P, and there is no change, so point P is equal to point Q, and r of t vector, or r of the parameter of t, is equal to r of t plus delta t, and that would mean then that r of d plus delta t minus r of t is equal to 0. There's no change here. And I should say equal to the 0 vector. If there's no change, we are at a single point in space. And if we are at a single point in space, then we don't have a derivative. So this is why we have to say that r prime of t cannot be equal to 0, because we have to have some change in our position. You might wonder, what does it look like? If r prime of t does in fact equal to the 0 vector. For this example, in which the position vector is given as t cubed for the x component, 3t squared for the y component, 1 over 6t cubed for the z component. At the point t equals 0, we do have a 0 vector for our position, and the derivative is also equal to the 0 vector. In this situation, what we have here is a cusp. And as you know from calculus, when we had a function of a single independent variable x, derivatives are not defined at sharp points. This sharp point right here, there is no tangent line. As you approach that point from the left, getting very, very close to the point from the left, the tangent line approaches vertical, slanted down and to the right. And if you approach that point from the right, the tangent line also approaches vertical, but along a different diagonal. One of those tangent lines has a positive slope. The other tangent line has a negative slope. These tangent lines, as they approach the cusp, approach an undefined slope from different directions, one with the positive sign, one with the negative sign. So at that point, we would say that this function is not differentiable if we are in our beginning calculus class. And the same thing here, we would say that our vector function is not differentiable at that point.